Hello viewers, welcome back to our series of lectures on solid state. In this last session on solid state, we will take up the experimental determination of crystal structure using X-ray diffraction. The session is planned as follows, that is, to begin with we will briefly review the contents of previous sessions. Thereafter, we will see that what are different experimental methods for the determination of crystal structure. In this process, we will briefly touch on Loess method, rotating crystal method, then powder diffraction method, then we will try to compare these three methods in terms of different parameters. Having done that, we will take up how do we index a given diffraction pattern. We will take up an example wherein we will take an experimental outcome of a given experiment and then try to see that how do I index that pattern in terms of the nature of the crystal and also the unit cell parameters on that. Then towards the end we will try to sum up what we do today. Now, let us make a beginning by recalling what we have done so far. What we have done so far is that we started by discussing different aspects of crystalline solids. Thereafter, we explained the concept of symmetry and discussed different operations of molecular and crystal symmetry along with the corresponding symmetry elements. We talked about symmetry in molecules, then we kind of moved on to that of in case of crystals. We found that differences between the two. Thereafter, we defined what is called as a lattice plane. Then we explain different ways of designating those planes in terms of Weiss indices and Miller indices, etc. And then also we have explained the principle of X-ray diffraction by crystalline solids, that is why does it happen that X-rays get diffracted by the crystalline solids. That is all what we have done so far. Now, we want to put all this into practice and then see how do I make use of this information to decipher the crystalline structure of a given crystalline solid. To do that, let us see what are different methods. There are three methods of determination of crystal structure and they happen to be Loess method, second is rotating crystal method, the third one is the powder diffraction method. We will talk briefly about each one of them and then see in what way are they the same or different. We will compare them towards the end. Now, Loess method is very simple. This method is the first one to be there. What it does is that we have a source of X-rays, then this X-rays are made to pass through a slit and then made to fall on a crystal here which is mounted on a platform there. Now, once this crystal, this X-rays fall on the crystal, they get diffracted as we discussed in the previous session. Then because of this diffraction, I get different points on the screen, the photographic plate which has been put on at a distance over there. And also there is a small provision here of a shield here, because the X-rays are not made to directly fall on this, because that has to be avoided, otherwise you will not get any meaningful pattern over there. So, there is a shield to not allow the X-rays to directly hit the photographic plate, only the X-rays, the secondary radiations which are coming as a consequence of diffraction, they are the ones which are made to fall on the photographic plate, and then this is made to where the diffraction pattern is coming, that is analyzed in terms of the structure and all. But what you find is that this method basically is using a single crystal there, and also the X-rays are polychromatic in nature, because we are just using a source of X-rays and then all possible radiations which are coming, they are made to fall on the crystal. We will talk about it a little more later. Then the setup is that got a fixed crystal, that theta is constant, because you have a crystal here, radiations are coming falling on that. So, the crystal is fixed. So, you are not making any change in the orientation of the crystal there. So, just all radiations are coming hitting on this and they are getting diffracted and we are getting a pattern over there. Thereafter, another thing which is important because of this is that because of different values of lambda, because the wavelengths are polychromatic in nature. So, different DHKLs will be diffracted at different directions there. Again, Bragg's law will become operative in this case. That means, depending on the diffraction this thing d values, you get different theta values over there. And this method actually provides information about the crystal geometry, but does not give anything about the crystal parameters. We cannot work out what are the parameters over the crystal, what is the kind of a lattice parameter of the crystal being talked about. Now, let us take up the second method, that is a rotating crystal method. In this method, what we do is we take a large crystal of the solid which is to be determined and then mount it on an axis, and then that is where we do it. So, the crystal is here and then we make X-rays fall on that, and then these X-rays get diffracted and they are kind of taken on a photographic plate which is mounted on the in a circular form over there. So, the diffraction patterns are coming onto the photographic plate, and then this plate is analyzed for the kind of a pattern which is being observed there. So, the important thing here is that once you have got a crystal layer, X-rays come, they get diffracted. Then there is only one orientation is there, only one set of planes will be in the path of it. Then what we do is we rotate the crystal. When we rotate the crystal, what happens is different sets of planes, different families of planes will come in the path of X-rays and they get diffracted separately. That means, for each kind of a thing, for each set of planes which are in the path of X-rays, there will be a diffraction coming over there. So, in the previous case what we had was, we had all radiations coming and this crystal was fixed. Now, we have radiation as fixed because our lambda is not changing, it is a monochromatic source, but my crystal is rotating at different angles. In the process, all kind of radiations are, all kind of sets of planes are coming in the path of radiation and they are getting diffracted there. Okay. Now, so as I just mentioned, the rotating crystal brings different sets of planes in the path of it, and then according to the Bragg's equation, we get suitable diffractions there. The angle theta at which we get the diffraction, that is then made use of to determine the kind of planes which are causing that diffraction pattern to be there, and then base of that planes we try to work out what is the nature of the crystal lattice I am dealing with. So, that is the way we go about it. We will actually do one analysis towards the end of the session here. Now, typically in case of a rotating crystal method, we have what is called as a theta to theta scan. What happens is, this just for sake of understanding here. So, this is my monochromatic X-rays which are falling on this. This is a set of planes here which are falling in the path of the X-rays here. So, this is my angle here theta at which the radiation is falling onto the set of planes and then it gets diffracted here. Again, this will be theta, but since if I look at this here, because this is the path of X-rays here, if it just continue like this, from this path this angle happens to be 2 theta. So, this is typically called as theta to theta scan, and then you have some kind of detection mechanism. Nowadays we can do it electronically, otherwise typically what we do is you put a photographic plate all around here, and then suppose I have one set of planes here, radiation will come and they get diffracted, and here there will be spot on the film here. We have another spot on this side as well, and so on and so forth. So, that spots are then analyzed to decipher the structure. Now, that is what I was trying to refer here. What you have is, this is coming, the falling on the crystal here which is rotating. As a consequence, different sets of planes are coming in picture, and then we get different kind of spots on this which can be opened and analyzed. That is how it looks like there. The third method is similar to the rotating crystal method, but it makes use of one more thing here. There is a modification here. The modification is that instead of using a single crystal which I mentioned earlier, it actually is a drawback of the rotating crystal method, because it becomes very difficult to get single crystals in all possible cases. So, what we do is we try to use what is called as a powder. We take a solid, crystalline solid, make a very fine powder of that, and in the capillary we fill that powder and put that capillary in the path of the X-rays. So, what happens is, so when this is my source of radiation, my X-rays are coming which are monochromatic here. I take one fine capillary filled with the fine crystallites there. When we take a crystal system, make a very fine powder, put into a capillary, put it in the path of it. When my X-rays are coming, now I do not have to do anything to this. Now, when I am putting a large number of small crystallites in the path of X-rays, so these crystallites are randomly placed. So, what will happen is, in different small crystallites, different sets of planes will be in a direction in the direction of they will be kind of getting exposed to the X-rays, and as a consequence they will give me a diffraction pattern there. That means, whatever I was trying to achieve in case of rotating crystal method, by rotating the crystal at a different at a certain speed, that all can be done in one shot. That means, this powder here has all possible orientations lined up according to the in the path of the X-rays, and they get a diffraction pattern. The pattern will be similar to what have in case of rotating crystal method, and then this method is better off because this provides an easy accessibility to getting the diffraction pattern there. Then what happens is, that is the way it looks like, because this is my X-rays are coming here. So, you have our specimen here, the powder here, and when the radiations are coming falling on this. So, this will be a 2 theta scan here, 2 theta kind of a diffraction there. So, that is the kind of cones will be formed on the, because this is my photographic plate which is all around the path of X-rays there, because this is my X-rays are going like this, and this is where my photographic plate is. So, when the radiation comes, falls on this, gets diffracted. So, one set of planes will give me this diffraction, another set will give me this diffraction, and there will be many such diffractions there in the forward direction as well as in the backward direction there. So, each one of them is captured onto the photographic plate, and then this photographic plate is cut open, and then we just spread it out. So, this gives me the where the X-rays are getting in, that is where the X-rays are getting out of it. So, we just that means you have a circular photographic plate, just cut it open, spread it out. So, what you get is the pattern of this kind. Now, that is the kind of pattern I will be getting there. That is one of the experimental outcome shown over here, and this pattern is then analyzed to obtain the information about the kind of unit cell and also its dimensions there. So, that is the kind of method we make use of. Now, let us try to compare the 3 methods. What we have here is we have got 3 methods, is rotating crystal method, powder diffraction method and Lois method. Now, in terms of crystal, in rotating crystal I am using a single crystal here. In powder diffraction I am using large number of crystallites, because I am making a small powder of the crystal there, and Lois method I use again a single crystal here. In terms of the kind of orientation part of it, how to manipulate the orientation of the crystallites here. So, in this case I am rotating the crystal, here I am keeping the fixed thing, because my powder is just in the path of the X-rays, and same is true over here also. Here I do not do anything to the crystal, I have fixed crystal and a single crystal which is fixed here. But the third thing is very important here, that in case of rotating crystal method I am varying the theta, because I am rotating it, I am making different angles, making the crystal to have different angles in the with the X-rays there, and then accordingly the diffraction pattern comes there. Whereas, in case of powder diffraction method, what you have is we make different orientations of the crystallites to come in the path of X-rays, whereas in the third case what you have is even the lambda itself is a variable, because here I am using a polychromatic radiation there. In both these cases it is monochromatic, but here it happens to be polychromatic radiation, even the lambda is the only variable. These two are fixed, the crystal is fixed, angle orientation is fixed, but only the wavelength which is a variable there, because I am using a polychromatic radiation there. This is all about different methods used for studying the X-ray diffraction of different crystalline solids there. Now, let us take up how do I analyze diffraction pattern. That means, what I have done is I have taken a crystal, put into the path of X-rays, got a diffraction pattern. So, what do I do with that? How do I analyze that? That is very important for us, because that is the crux of it, because all that what we were doing so far was just to make a basis for this to be achieved, that how do I analyze a diffraction pattern in terms of, because my objective is to find out what kind of crystal I am dealing with, what are the parameters of this, what is the nature of the crystal there. Okay, let us take an example here, and to do that example, let me first make the basis of this analysis in terms of what we learned so far. In any typical X-ray pattern, there are 2 parameters which are important. One, the position part of it, that is where exactly is that signal being obtained, where exactly is my kind of diffraction point is coming there. Okay. So, that is the position, and that position determined by the size and shape of the crystal. And second is intensity, which is determined by the atomic positions within a unit cell. That means, what kind of a unit cell is there, and what is the nature of the diffraction point there, the lattice point, what is the nature of that, whether it is a smaller atom, a larger atom or whatever. So, intensity is determined by that, and position is determined by the nature of unit cell and the size of unit cell there. So, there are 2 things which we will be making use of. In order to make use of the diffraction pattern, to index that and to get information from there in terms of the nature of the unit cell and the dimensions of that, we need to find some kind of a interlinkage between the diffraction pattern I get and the interplanar distances there, and that we can do as follows. That is, we know that for a cubic crystal the interplanar spacing or the DHKL is related that indexing parameters there, the mirror indices as follows, that is 1 by d square to be equal to h square plus k square plus l square by a square, where a happens to be the cell dimension and h, k, l are the indices of the planes in question there. Now, if I just rearrange this equation and try to correlate with the Bragg's law we know is for the first order diffraction lambda to be equal to 2 d sin theta, where d is nothing but my d h k l. And if I just rearrange this equation, I just take square of this gives me lambda square to be equal to 4 d square sin square theta, or I can just rearrange that and get sin square theta to be equal to lambda square by 4 d square. Now, this I just combine the equation 1 and 2. When I combine equation 1 and 2, I can just get 1 by d square to be equal to 4 sin square theta by lambda square. This is simple mathematics there. And or in other words, I can do a little more simplification and see that sin square theta to be equal to lambda square by 4 a square and then h square plus k square plus l square. That means, this actually is a constant here, which is of use to me, or I can even put it like this, that sin square theta divided by h square plus k square plus l square to be equal to a constant k. This is lambda square by 4 a square. I can typically they are called as a constant k here. Now, what you see is that this is the diffraction angle at which I am going to get my point there, and h, k, l are the indices of the planes which are causing that. And then this a is my unit cell parameter, that is the unit cell dimensions there, and lambda is the wavelength of the X-rays being used there. So, that is a kind of formula which I am going to make use of. An important point here is that sin square theta by h square plus k square plus l square is a constant. This constant is important for me, which I am going to make use of. Okay. Now, if this be so, then what do we do is, we know that the possible reflections, if I just take a simple cubic system, let us see how do I make use of this formula. For a simple cubic system, what do we have is, we have the table gives you the kind of indication about what is the possible values of h square plus k square plus l square. For the plane 1 0 0, that number will be just 1, because 1 square is 1 plus 0 plus 0. Similarly, in this case of 1 1 0, it will come out to be just 2. For this it will be 3, and so on and so forth. This will be the kind of things at which I am going to expect my diffraction points there. You find that in this case there is no 7 here. You have 1 2 3 4 5 6, then 7 is missing, because then you got 8 9, and then this will be 9 again and 10 and so on and so forth. There is no 7 here. If you continue like this, you find there is no 15 also. The reason for that is that there is no possible combination of h square plus k square plus l square. That means, some of the squares of 3 whole numbers cannot be 7 or 15. So, they will not be there. This has a very important implication. That is this kind of a pattern. That means, if I have a simple cubic system and if I take diffraction pattern, so the values of h, k, l which I am going to have, the squares of that can have only these possible combinations. That means, it is a characteristic of the primitive cubic system or the simple cubic system. Now, when I move on to say this is my face centered cubic system here. In case of face centered cubic system, what you find is this lattice has got 2 0 0 planes, right. These are the ones, the shaded planes are 2 0 0 planes, and they are, if you look at, we talked about Miller indices in the previous session. Now, look at this plane here, this is my 1 0 0 plane, and the 2 0 0 plane is at half the distance of 1 0 0 plane. So, what will happen is, because when the diffraction takes place from 2 0 0 planes, that diffraction will be 180 degrees out of phase with the ones which comes from 1 0 0 plane. That means, since they are out of phase, what will happen is they will get destroyed there. As a consequence, this reflection from 1 0 0 plane will not be observed in the diffractogram, though the planes are there, they are getting, the refraction is taking place, but because of the cancellation of the diffraction by 2 0 0 planes, I will not be getting this point in the diffraction pattern there. Now, similarly, what happens is, if I take different types of crystal systems, I will find that there will be some certain characteristic absences there, and these absences are very very important for us, because they are the ones which give us indication about the nature of lattice I am dealing with. So, these actually help us in indexing the type or indexing the pattern to find out the type of unit cell what we have in the system there. Now, this is basically a kind of a compilation of the allowed reflections for cubic systems. What it says is, for a primitive cubic system, as we just saw, the diffraction pattern, the diffraction points which I will be observing will be the ones which will be corresponding to the combination as follows, where h square plus k square plus l square happen to be 1, 2, 3, 4, 5, 6, 8, 9, 10 and so on and so forth, because I will not have any other possibility from simple cubic system. Similarly, for BCC system, I will have the diffraction pattern will be coming only when h square plus k square plus l square happen to be 2, 4, 6, 8, 10, 12 and so on and so forth. That means you find that any combination which gives you an odd sum of the 3 squares will not be observed. For FCC, the numbers happen to be 3, 4, 8, 11, 12 and so on and so forth. They are very characteristic patterns there, and these characteristics are the ones which are actually exploited to decipher the diffraction pattern from a given cubic crystal there. So, this is a different representation of the same thing there. This just tells you that what are the possible planes there which are causing the pattern which is to be observed there. You can see that for FCC, it is only a few lines will be observed there. For a simple cubic system, we got a large number of lines will be coming there, only thing will be 7 and 15 will be missing. Okay. So, that is what we have to keep in mind. Basically, all this boils down to saying that from this whole analysis we have done, that in order to get meaningful information from the diffraction pattern what we got, we basically need to know two things there. One, what is the combination of h square, k square and l square, or rather HKL, what is the designation of the planes which are causing the diffraction pattern as we have got. So, that means we need to determine h square plus k square plus l square. So, we had this equation sin square theta to be equal to k h square plus k square plus l square, wherein k is a constant which is equal to lambda square by 4 a square. Lambda is the wavelength of axis used and a happens to be the unit cell parameter for a cubic crystal. Now, essentially to make sense out of the diffraction pattern I have got, I need to know what is the value of k, because that is going to give me, because lambda I know of from the source I am using there, and I can get the value of a from k. And if I get to know about h square plus k square plus l square, I will be able to work out what is the nature of the unit cell. So, both the information are going to come from this equation. How do I get information is, what we do is, we do the experimental value, what I find is the 2 theta value, divide by 2, I get the theta value. I take the sine of that, square of it. So, I take sine square theta for each peak what I observed in the pattern there, and divide that by integers 1, 2, 3, 4, 5, 6, 8, 9, 10 and so on and so forth. So, by dividing that, what I get is, I get a constant value k that is to be used at a later stage. Once I get the value of k, and sin square theta is known to me from the observed values of the diffraction pattern. So, from this I can use these two things to get the value of the possible values from where the diffraction pattern is coming, the values of h square plus k square plus l square. So, I can determine this also. Once I determine this, that gives me idea about the HKL values there. Once I know the HKL, that means what are because that here I am going to make use of the so called absences in the pattern there. So, from that I can work out the lattice type there. So, that is what I am going to make use of. Now, we will actually take up an example and see how do I get the information about it from a diffraction pattern. But before that, let me just work out the sequence, the steps which are used for deciphering the structure of the unit cell and the cell parameter from the diffraction pattern. The sequence is as follows, that is, we first determine the 2 theta value from the observed peaks. That is a very simple thing, there is a tools of measurement over there. We measure 2 theta value, then divide by 2, get the value of theta, then calculate sin square theta, and from this we compute the ratio sin square theta by integers as I just mentioned 1, 2, 3, 4, 5, 6, 8 and so on and so forth. Do that. Having done that, by this process we should be able to get the value of k. We find out the lowest common quotient from there. We get the value of k, then you take the sin square theta value for each peak what you have got and divide that by this value k, and that in turn gives me the integers combinations, that is h square plus k square plus l square. Once I get this, then I can try to use this pattern what I get there to identify the lattice type there. Once I get the lattice type, then using k I can find out the lattice parameter, that is A. Now, these steps, there are 6 steps to be done. Let us take an example and then try to see how do I get information from there. The example is as follows. The diffraction examination of polonium using 71 picometer molybdenum X-rays gave lines at the following values of 2 theta. That 2 theta is what we measured actually. So, they are the values given to us. So, the objective is to identify the unit cell and also to find out the unit cell dimensions or the value of A. How do I go? Let us go stepwise now. Our step 1 was determine the 2 theta values which are provided to us. So, we skip this one. Step 2 is calculate sin square theta and from it compute the ratio of sin square theta by different integers. How do we do that is the data is given over here. These are my peak positions, they are the corresponding to theta values. I divide that by 2, get the value of theta, take sin square, get the value of sin square theta. So, they are the values I get there. Thereafter, what do I do is I compute sin square theta by 2, sin square theta by 3, 4, 6, 8 and so on and so forth. When I do that, I get certain data of this kind. That is my step 2. That means, I compute sin square theta from the observed values and then try to compute all these ratios over there. The step 3 is to identify the lowest common quotient in this. So, this has been marked in blue here. So, from this whole data I just visually try to identify. So, you find that this is 0.011067, 0.011073, 0.001. That means, typically we find that they are the common denominator over there, the common quotient over there. The value happens to be 0.0111 to the 4th decimal place. So, that is the value of k for me. That means, that is the value of k I determined in step 3 there. Once I get the value of k, what do I do? My step 4 was, that means, I take the value of sin square theta what I got in my step 2 and then divide that by the value of k. When I divide the value of sin square theta by the value of k, what do I get? In this case, it comes out to be just 1. This is 1.96, which is basically if you just round off, it comes to be 2. This is 3, 4, 5 and so on and so forth. So, what I find is that if I identify this, that the observed values of s square plus k square plus l square come out to be 1, 2, 3, 4, 5, 6, 8, 9, so on and so forth. We find that this pattern corresponds to a simple cubic lattice. Had it been say BCC type structure or FCC, then would have got certain things missing over there. So, in this case 7 and 15 are missing. Okay. So, by just looking at what is the value of this pattern coming there, it is just 1, 2, 3, 4, 5, 6 is coming there. So, this basically corresponds to, it is just incidental that we try to work out our starting point in terms of simple cubic system, and this happens to be simple cubic system. So, we conclude that polonium belongs to a simple cubic lattice there. Now, our next objective is to find out the value of lattice parameter, that is value of A. We know that the value of k to be equal to lambda square by 4 a square. I just rearrange that, my A comes out to be lambda square by 2 square root k. K I know it is 0.0111 and lambda is given to me. I just substitute the values, we get the value of A to be equal to 337 picometer, and that is the value of unit cell parameter in case of polonium. So, that is how we try to make use of diffraction pattern to get information about the unit cell and its parameters there. Now, let us make one more important point here, because there are two very common crystalline solids we have is sodium chloride and potassium chloride. Both crystallize in terms of FCC lattices, but the kind of diffraction pattern they give, they happen to be different. What happens is, in case of NaCl, the diffraction pattern comes out to be what is expected of an FCC lattice, whereas in case of KCl, what you find is the diffraction pattern looks more like that of a simple cubic system rather than FCC. The reason for that is that the second point which we have not talked so far is, that is what we have done so far is that the diffraction pattern we have tried to see only in terms of the nature of unit cell. But what happens, because NaCl and KCl both are FCCs, but the difference in sizes, sodium and chloride ions, sodium ions and chloride ions are much different in size, whereas potassium ion and chloride ion are identical in size. As a consequence, the scattering power are identical. So, because of this very reason that the pattern comes out to be more like that of a simple cubic rather than of a face centered cubic. It is just because of because we are not able to distinguish between the two kinds of ions. So, though they are FCC, but it appears to be simple cubic. But if we do more detailed analysis of the diffraction pattern, we find that even KCl also has got an FCC lattice. The only thing is we are not able to distinguish on the basis of the diffraction pattern what we get there. Okay. Now, it is time that we sum up what we have done today. What we have done today is that we briefly reviewed the contents of previous sessions. Thereafter, we described different methods of experimental determination of crystal structure and compared them, because there are three methods we talked about. Having done that, we explained the basis of indexing diffraction patterns for a cubic crystal, and thereafter we have outlined a strategy. There are 6 steps in that, by which we can try to decipher the structure, the kind of unit cell, and also the unit cell parameter on the basis of diffraction pattern there, and also we took an example and demonstrated that how this strategy is made use of. With this, we conclude our discussion on the topic solid state, and I hope